Well, tonight we're going to study relative extrema, and we're really going to start to put the derivative to use tonight and make it work to our advantage as we try to investigate the behavior of some really wild functions. So first of all, a relative extrema is just a term we use to refer to both relative maximums and relative minimums. And as we go through the video, we'll also sometimes call them local maximums or local minimums, and that's just another way of saying relatives. So as we look at this first picture in front of us, we're going to start on the far left here and move from left to right and identify right here we've got ourselves a relative max, and all we're saying is relative to the points immediately before and immediately afterwards, it's the biggest one in that local neighborhood. And then we've got a relative min down here, again relative to the points immediately prior and immediately afterwards, it's the minimum point. Let's see, up here we've got a relative max. We've got another relative min here at x equals 2, a relative min there, and at x equals 4 it's a relative max. So we're just saying like local to this guy's neighborhood or relative to his proximity, he's the biggest point in that interval. Just a little more practice getting used to some basic graphs here. Just to reiterate officially, a relative or local extrema, it refers to both the relative max and the relative mins of a function. So if they ever told us to find the relative extremas, we'd have to go find both all the maxes and all the mins. First of all, let's focus on maximums, and these graphs are a little tough to read, so we'll just assume that they're all scaled by 1. And we've got, right here, we've got a relative max, and what you'll notice is if we draw a tangent line, it'll be perfectly horizontal. So what we're going to say is that f prime equals 0. And now f, this is just for fun, it refers to the height of the graph, and at that location, the height would be, looks like a 2. Okay, next one here, right here we do have a relative max. The function's continuous, and within that neighborhood, he's definitely the tallest one. Now the derivative in this case is undefined, or it doesn't exist. We'd say the curve's non-differentiable right there, and that just means it's two-pointed. It's very, pricky and pokey right there. At the f, though, the height of the function looks like it's a 3. Next one, we've got another relative max, and again we would say that the derivative doesn't exist. It's too sharp, it's not smooth enough to be differentiable, so we'd say non-differentiable again, and the height just happens to be -1. Alright, moving on to our relative mins. Let's see, I've got a relative min right here, and the curve is very smooth, and that's a turning point. We're going to say, because that tangent line is horizontal, the slope is 0, and f of x just happens to be a -3. Let's see, again, very pricky, pokey right there. It's a cusp, we'll call it, just like the one above it. Again, this was a cusp, and all that means is that the curve is non-differentiable, so we'll say f prime does not exist, and the f of x is -1. And over here again, relative min, derivative doesn't exist, too sharp, and the height looks like it's -2. So what did we learn from these real quick examples? In other words, what did all the relative maxes and mins have in common? One of two things has to be true. Either the derivative is equal to 0 or the derivative is going to be undefined, and that's going to be true for all relative maxes and mins. Here's a great definition we need to toss in our notebook, and it's a definition of what a critical number is. And a critical number is an x value where the derivative is equal to 0 or undefined. Now I really want you to emphasize undefined. Historically we've been great at setting the derivative equal to 0 and finding those points, but we also always want to entertain the idea when will the derivative be undefined, aka setting the denominator equal to 0, and that'll tell us when it's undefined, and those are where the relative extremas could occur, and that's huge. And I guess what we're saying there is if you had a function like x cubed, there does exist a horizontal tangent line, but it didn't necessarily guarantee there's a max or min. It means there's a strong likelihood of a max or min, but not a 100% guarantee. So what we're going to do here is we're going to practice a couple of examples. We're going to find the critical numbers, and I'm going to start with this one right here, and we'll call this example number 1, and then we'll put example number 2 on another slide just to make sure we've got enough room. So what I'm going to do is I'm going to always start off by taking the derivative in terms of x, and that's going to give me 4x cubed. One of the nicer, friendlier derivatives we've seen in some time, some real basic power rule. And now what I'm going to do is I'm going to try to set that function equal to 0, which means I'm going to have to factor it as best I can. I'm going to factor out the GCF of 4x, x squared plus 3x plus 2, and we'll continue to factor it, being careful not to lose that GCF. And now we'll tee it up. And let's say when x equals 0, when x equals -2, and when x equals -1, those are the 3 critical points. They all happen to be horizontal tangent lines. These are the locations of the horizontal tangent lines. Now, example number 2 is going to be significantly messier, and again, the directions want us to find all the critical points, so we're going to figure out when is the derivative equal to 0 and when is the derivative undefined. And the first thing you'll notice is as we get ready to take the derivative, it requires product rule. So I'm going to say the first times the derivative of the second, and I got to finish that chain rule by a multiple of 2, plus the second times the derivative of the first, and that's going to be 1/2 x raised to the -1/2 power. All right, so we got a lot of arithmetic here. It's real heavy on the algebra part. I'm just going to take my time and kind of clean this up. I've got looks like 8 radical x times the quantity 2x minus 4 cubed, and I'm just going to put that over 1. And because I know this next one's going to be a fraction as well, and we'll go 2x minus 4 to the 4th all over 2 radical x. I need a common denominator, so I'm going to multiply the first one by 2 radical x on top and bottom. And let's see, that's going to give me 16x, quantity 2x minus 4 cubed plus 2x minus 4 to the 4th. And I'm just going to go ahead and put that in one big fraction all over 2 radical x. So the first thing I noticed right now is I already know where one of my critical points is going to be. I know that x equals 0 is going to be one of my critical points because if x was a 0, the denominator would be 0, and so that forces the derivative to be undefined. To find the rest of the points, we're going to go ahead and we're going to factor out a GCF in the numerator. And my GCF is going to be the quantity 2x minus 3 to the 3rd. Factoring out a GCF, I'm going to divide this first term and get a quotient of 16x. Plus, I'll divide that second term by the GCF of 2x minus 3 cubed, and I'll get 2x minus 4. Whoa, that should be a 4 right there. I just caught that. All right, to the first. And last but not least, we'll just combine those like terms. And that's going to give me 18x minus 4. And all I need to do now is I want to set the derivative equal to 0. Basically just setting the numerator equal to 0. And what we're going to discover is because of this term right here, we're going to get x equals 2 as a critical point. Because of this term right here, we're going to get x equals 2/9 as a critical point. And then because of this term right here, we're going to get x equals, x equals 0 as a critical point. So these two made the derivative equal to 0, and this one right here made the derivative undefined. So those are my 3 critical points. Well, now that we've really drilled in what a critical point is, we're ready to move forward, and we're going to introduce you to what we call the first derivative test. And this bear is extremely useful. We're going to use this probably a million times by the time we get to May. And basically, the first thing, let's just talk about intervals when the function's increasing and decreasing. All right, and first, we're always going to test the intervals between those critical points. So that's where we're going to start to make number lines. So we're going to have number lines coming out our ears. And here's what's going to happen. If f prime is positive, that means f, the original function, is increasing. And let's take a look at that. We can all agree that this is an interval where f is increasing, and I think you'll agree that all of the tangent lines have positive slopes. So we're saying f prime is positive or greater than 0. I think you'd also agree that here's another interval where f is increasing, anywhere from -1 to +2. So again, we're thinking positive slopes on our tangent lines. F prime is greater than 0. And then there's one more interval over here from x equals 4 all the way to infinity. We've got positive tangent lines again. All right, let's break out another color here. And it would say if f prime is negative, then f, the original function's decreasing, and I think you'd agree derivative's negative, 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 and again over here negative, 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 negative. So whenever the slopes are negative, the original function f is decreasing. All right, now how do we find a relative max or a relative min? Here it is. If the derivative of a function changes from positive to negative, like what's happening right here, at that instantaneous moment, the derivative is in the process of changing from positive to negative, we'll say there is a relative max at that critical point, okay? And of course, everything's assuming it's continuous. And then we'll switch gears. If the derivative changes from negative to positive, like what happened right here, that this instantaneous moment, the derivative is in the process of changing from negative to positive, we're going to say there's a relative min. And those are the justifications we're going to use. We're going to talk about the derivative changing from positive to negative or from negative to positive to justify all our answers. Okay, here we go. We're going to put it all together here, and we're going to use the first derivative test to answer all these questions. We want to find out when f of x is increasing, when he's decreasing, and then we're going to find the coordinates of all relative extrema, which means we got to find both the maxes and the mins, and we're going to really work on our justification to say, okay, what's the AP exam? What are they looking for in order to ensure we can get full credit? So first of all, we're going to calculate that derivative because we want to go find those critical points. We can't use the first derivative test until we find those critical points. And it looks like our derivative is 4x cubed minus 16x. We've got a beautiful GCF of 4x, which is going to leave us with x squared minus 4. And by the time we set that equal to 0, we're going to get critical points of 0 and plus or minus 2. X equals plus or minus 2. So we got 3 critical points. And we could also say because there was no denominator involved, the derivative will never be undefined. So here's what my sign chart looks like. And I'm very, very picky about sign charts. I think we should take a lot of pride in our sign charts. We're going to put the values of f prime on top, and we'll test the values of f on the bottom. Critical points are negative 2, 0, and positive 2. And what we're going to do is we want to examine this interval from negative infinity to negative 2. And we're going to pick any random number in that interval that your heart desires. Say we pick like a negative 3. And we plug it back into the derivative right here. And 4 times negative 3 is negative. And then over here in the parentheses, we could say that 9 minus 4 is positive. And a negative times a positive is going to give us negative values. Therefore, f is decreasing within that interval because f prime's negative. Next thing I need to do is I need to test the interval between negative 2 and 0. Your favorite number is probably going to be a negative 1, so let's go plug that in. 4 times negative 1 is negative again, and 1 minus 4 is negative. Negative times a negative is generating positive f primes, which now means f is increasing. So we can conclude right now that at x equals negative 2, there's a relative min, and I use a lowercase m for my mins. All right, next interval. We're going to test a number between 0 and 2. Probably positive 1 is going to be the friendliest number. 4 times 1 is positive. 1 minus 4 is negative again. Positive times a negative is negative. We just proved that f's decreasing, and we just proved that at x equals 0, there's a relative max, capital M for max, and we'd say there's a max because f prime changed from positive to negative. Last interval, from 2 to infinity, I'm going to test a 3. 4 times 3 is positive. 9 minus 4 is positive. Positive times a positive is, again, positive. F's increasing. So because the derivative just changed from negative to positive, there's a relative min. I'll go lowercase m. Now, what's the AP exam looking for? And they're asking me, where are the relative extremas and so forth. Okay, here's what my first sentence looks like. There is f has a relative max at x equals 0 because f prime changed from positive to negative. All right, that's exactly the sentence I'm going to write. Doesn't have to be any fancier than that. That's just very concise and to the point. And then how about relative mins? Let's say f of x has a relative min at x equals negative 2 and x equals positive 2 because of y? Because that derivative just changed from negative to positive, and that's our blueprint. Okay, new example. We're looking at g of x, same directions. They want to know on what intervals is g increasing, when is he decreasing, where are the relative extremas. So again, we can't even touch that discussion until we find the critical points. So we're going to go ahead and we're going to take the derivative. Now again, I'm picturing g of x as being x to the 4/3 plus 4 times x to the 1/3. So that's what I'm rewriting it. Now we're ready to derive, and we'll say 4/3 x to the positive 1/3 plus 4/3 x to the negative 2/3. Now as we try to clean this bear up, I'm going to rewrite them as fractions. I'm always a big fan of that. 4 times x to the 1/3 over 3 plus 4 all over 3 x to the 2/3. What I'm going to do is I'm going to multiply the first fraction by x to the 2/3 top and bottom, and that's going to create my common denominators that I need. And let's see, that's going to be, add those exponents, I'll get 4x to the first plus 4 all over 3x to the 2/3. Now believe it or not, there's going to be two critical points. First of all, g prime is undefined at x equals 0, and I just did that by setting the denominator equal to 0. And then I'm going to also figure out when g prime is equal to 0, which is setting the numerator. And that'll give me x equals -1. So let's say that -1 and 0 are my critical points. G prime's here, g's on the bottom. Now the other thing you might want to do is, I don't know if this is helpful at all, but I do cubed root of x squared. And what's happening is, by the time you end up squaring this rascal, you're guaranteed to be positive. So when I go to test certain points, I already know my denominator is positive, so I'm just going to worry about the numerator, whether that's negative or positive or not. Okay, first interval, somewhere between -infinity and -1. I'm going to pick a -2, plug it in. Let's see, -2 plus a 1, that's negative for sure. So g's decreasing. And let's see, I'm going to pick, between -1 and 0, I'm going to pick -1/2. Let's see, -1/2 plus a 1 is going to be positive. So we're all good there. And then somewhere between 0 and infinity, I'm going to pick a positive 1. And 1 plus 1 is going to be, again, positive. So we know that g was increasing here and increasing here. So something a little strange has happened here at x equals 0. It is definitely a critical point, but what we do is we say it turns out to be a false critical point because the derivative never changed signs. It was positive prior to 0 and it was positive after 0. So there's neither a relative min nor max right there. It's just a false critical point. And I'm going to say that -1 was the only extrema, and there was a relative min right there because the derivative changed from negatives to positives. So let's go ahead and write our sentence. We'll say g of x has a relative min at x equals -1 because g prime of x changed from negative to positive. Let's see if we can squeeze it in there. Oh yeah. Okay, I've got one more last treat for you here tonight. This one, I'm going to turn you loose, and I'm just going to let you guys try this function right here. We're going to use some quotient rule, of course, to find that derivative. And we're going to find all the critical points, and then make a sign chart to determine where the relative mins are, if there are any, and where the relative maxes are, if there are any. Again, and you'll notice they're using the word local here, but that's the same word as the word relative. It means the same thing. We're going to practice justifying our answer with some great sentences, and that's how we'll start off our class by just discussing our results on this question. So good luck, and I'll catch you tomorrow.